A massive coal plant cleans up its act and lights up millions of homes with explosive power. This mega roller coaster cranks up the biggest scare for your buck. A thrill machine that runs on gravity. A half-megaton telescope takes intergalactic snapshots from millions of light years away. And a pin-setting robot cleans up our game with surgical precision. Let's take a look inside these machines and see how they work. This is Drax, a coal-fired power plant in England. The size of 2 Manhattan Central Parks, side by side. This machine puts out almost 4,000 megawatts of power, enough to light up 5 million homes. This new-style coal burner has found a way to process and burn an old-style fuel. And it does it so efficiently, it's now among the cleanest mega coal plants in the world. Let's see how it works. Drax burns up to 36,000 tons of coal every day. That's 26 train loads. The trains dump the coal into giant hoppers. They slow down, but never stop. Every month, they dump enough coal to fill a 70,000-seat football stadium. But Drax doesn't burn chunks of rock. It's not explosive enough. So, it converts the coal to dust. A network of conveyors sends the raw coal to these pulverizing mills. Each mill has 10 one-ton steel balls packed together on a track. Coal drops into the mill through here, and the ring of balls crush the rock. A single pulverizer makes 36 tons of coal dust in an hour, and Drax has 60 of them. The coal dust is now an explosive fuel, lit up by propane and oil burners. This coal, dust, and air mixture burns at over 2,000 degrees Celsius. Each boiler is a mega kettle with flames 5 stories high. 10 stories above the flames, inside a network of steel tubes, water transforms to high-pressure steam, hot enough to melt lead. Drax is now ready to generate some serious electricity. The steam heads to the turbine hall. The turbines are housed in 6 units, each the size of a locomotive. Inside, 5 steam turbines. Each spins a drive shaft connected to a generator. When the steam hits the turbines, its explosive pressure spins the blades at 3,000 RPM. The blade tips travel at 1.5 times the speed of sound, pumping out 1,000,000 horsepower. That's the same as 6,500 passenger cars. So, burn coal, boil water, make steam, and spin 300 tons of stainless steel at Mach 1.6 to create 23,000 volts of electricity. Voltage measures how powerfully electrons flow through a wire. And Drax needs much more than 23,000 volts to get power to its millions of customers. To ramp up its voltage, which helps electricity travel great distances, you need a transformer. Drax runs the 23,000 volts through a series of copper wire coils, each wound around an iron core. That creates a magnetic field. Power jumps from one coil to another. When it goes from the looser coils to the tighter ones, the voltage increases. The transformers at Drax take the 23,000 volts from the turbines and step it up to 400,000. Which is great for the national grid. But what about this stuff? Burning coal is dirty business. It belches out harmful gases that cause smog and acid rain. Drax captures 90% of these toxic emissions before they hit the atmosphere. Smoke blows into these electrostatic precipitators. Toxic particles cling to these metal plates like fridge magnets as the smoke passes through. But that filtered smoke still contains sulfur, the culprit in acid rain. So, before it's sent to the smokestack, it's cleaned again. Every week, 10,000 tons of limestone is crushed into powder and mixed with water to form a slurry in this giant blender. When smoke is pumped through the slurry, sulfur is chemically locked into it. The resulting combo makes 750,000 tons of gypsum every year. The stuff that makes drywall and plasterboard. There's one last problem. The power plant still has huge amounts of steam to deal with. Once it's done powering the turbines, the steam needs to get back to the boilers for reheating. But first, it needs to turn back to water. So, the steam tubes are cooled by an outside source, a heat exchanger that uses river water. Drax uses 160 million liters of it every day from the river Ouse. But while cooling the steam tubes, the river water heats up to the boiling point. To protect the local ecosystem, it has to be cooled before being returned. Enter the cooling towers. Drax has 12, 2 for each boiler. The base of each one could hold the dome of St. Paul's Cathedral. The heated river water is piped into the 20-story towers, then drops through tightly woven plastic and turns to a fine spray. As heat rises, the towers draw a cool draft from the bottom and up through the falling droplets. The cooled water drops into ponds at the base of the towers and releases back to the river, cleaner than when they took it out. 36,000 tons of coal burnt up in a day, recovering most of its toxic emissions. This machine has always been powerful, but recent innovations have turned it into one of the cleanest plants of its size in the world. An over 1 kilometer track built on 20 stories of concrete and metal. The Ride of Steel is a machine designed to give you the biggest scare of your life. Doing 120 in an open-top mini train is scary enough, but not nearly as frightening as this. For 2 whole minutes, you're locked into a bucket on wheels. The job of this machine is to keep you alive, with no engine, no steering, and no brakes. Here's how it works. You're on your way, and the initial climb slopes gradually to a height of 65 meters. 12,000 well-oiled moving parts make up the large gear and chain assembly that pull you to the top. While butterflies churn in your stomach, Any one of those parts can snap without warning. But over 40 sensors monitor the climb. And if the chain breaks, magnetically controlled safety locks stop the train within seconds. The first hill on a roller coaster is always the tallest. It has to be in order to harness enough gravity to launch you 1,600 meters to the finish. 50 seconds into the ride, the train free falls into a near vertical drop. Zero to 120 in under 2 seconds. Way faster than most dragsters. As you drop, you're weightless. Any falling body weighs nothing while in free fall, until it hits something. Fortunately, you're locked in by the lap bar. Without that, you'd be airborne, flying 3 stories above the track. The force exerted on the cars as they corner around the track is more powerful than what's experienced on a space shuttle launch. So, to keep the train on the track, the undercarriage has 3 sets of wheels built in all directions to handle every dimension of flight. These are the load wheels. During the most intense maneuvers, they absorb nearly 4 times the weight of the car. That's over 50 tons of force. The guide wheels keep the car centered as it shifts from side to side. And the upstop wheels grip the car on the track during its most extreme maneuvers. 65 seconds into the ride, you're halfway through. Just when you think you're slowing down, you hit the Ride of Steel's double helix at 100 kilometers an hour. And while your brain thinks it's going in a straight line, your body is lashed to a train that is clinging to the edge of a circle. Up to 4 times the normal force of gravity pins your body down. That cell phone in your pocket now weighs as much as a kilogram. You've been flying for almost 120 seconds, and the end is rapidly approaching. Remember, this is technically a runaway train. It has no brakes. And you've got to stop in under 3 seconds. You're going off the rails. Regular brakes on this train would tear the cars apart. So the designers decided to stop the train from the outside. And they used some of the most powerful natural magnets in the world to do it. When copper fins fixed to the sides of the train slide through the magnets, they create a swirl of opposing currents. This magnetic braking stops the train in just 2.8 seconds. The designers of the Ride of Steel had a plan. Build a giant machine, insert humans, scare them half to death, and bring them back alive. And it worked. When scientists peer through a high-powered telescope, they may like the view, but they always want a better one. So, they came up with this. It's called the Large Binocular Telescope, or LBT. It probes deeper into the cosmos than any other instrument, and it has 10 times the resolution of the Hubble Space Telescope. A telescope is basically a magnifying glass. It focuses light that enters here onto a single point. In this case, a mirror located here. This bounces the light to an eyepiece that magnifies it even more, up to 60 times. That's pretty good, but its vision is still limited. Big glass lenses are hard to make and distort light, which is why the best telescopes use mirrors. Set 3,000 meters up this Arizona peak, the machine took 2 decades to build. It's a new generation telescope that reaches the edge of the universe, hoping to shed light on some of its unsolved mysteries. That's a tall order, but it's a big machine. The LBT is 2 telescopes in one. With its giant pair of binoculars and 2 of the world's largest mirrors, 16 tons apiece, spanning 8.5 meters. Working together, they capture more light than any telescope ever built. Starlight bounces off the two primary mirrors onto two smaller secondary mirrors, and then back down through this center hole to where researchers can see it or record it. But all this size doesn't do much for resolution. So LBT has to overcome the three optical challenges of any Earthbound telescope: keeping up with the rotation of the Earth, fighting gravity that distorts the shape of thin mirrors this wide, and keeping focus through the density of the Earth's atmosphere. First challenge, get a fix on a target and compensate for the Earth's rotation. This half-megaton machine has to position itself within 1/1,000,000th of a centimeter. That's about the thickness of a strand of DNA. May sound crazy, but it's done with this altitude azimuth mount. One axis turns with the Earth, the other tweaks the elevation. A point-and-control system translates the location of the object in the sky into geographical coordinates and locks into them as the Earth moves. The entire telescope incrementally shifts on two giant C-shaped mounts, like a big rocking chair, floating on a super slick film of oil. It's so perfectly balanced that all it takes is a set of 4 puny lawnmower-sized motors, one on each axis, to spin the heavy LBT a full 360 in just 4 minutes. The outer building rotates in sync with the telescope as it rides on its own rail system. And it does it to within 1.5 degrees of accuracy, even in gale force winds. The second optical challenge it needs to solve is gravitational distortion of the primary mirrors. The mirrors are so large, so thin, gravity actually warps their perfect parabolic shape. To correct this, there are 160 computer-controlled actuators underneath each primary mirror. These are like pistons that push up on the mirror to correct its parabolic shape and restore the image. The third optical challenge for the LBT is correcting distortions caused by the atmosphere. Stars don't really twinkle. It's the effect we see through atmospheric turbulence or haze. To lock that star's image into a single steady point of light, LBT locks onto a reference point, like a bright star that's already known. Computers measure the real-time angular distortions in the star's image to determine how much and what optical adjustments are needed to correct those distortions. 672 magnetic coils line the back of the hair-thin secondary mirrors. Each coil moves the surface up and down 1,000 times a second. The adaptive mirror surface actually distorts in real time to mathematically compensate for the angular distortions on the reference image. With the 3 major optical challenges figured out, the LBT has one more trick to help it see better than ever before. It ramps up its image brightness by swinging this pair of third mirrors into place, combining its binocular images into one super bright picture. That results in images like this nebula, over 113 million billion kilometers away. The LBT is the most powerful single-mount telescope in the world. A heavy, rock-solid machine tamed by precision feather-touch controls. Its sole purpose is to capture and translate light into pictures of places we can only dream of visiting. "95 million people all over the world throw a ball like this one and knock down billions of pins year after year after year. Not that long ago, teenagers used to reset these pins by hand, but that left restless bowlers waiting for the next shot. This robot is about to turn 50, and it never stops working. No lunch break here. It's cheap to run, doesn't suck up a lot of power, and it's fast. The Brunswick A2 pin setter can sweep up and rack a set of pins in just 9.2 seconds without fancy software. Just 4,000 moving parts that run like a clock. Let's see how it works. A typical throw will launch the 3 to 7 kilogram ball into pins made from hard rock maple at over 30 kilometers per hour. The pin setter waits for its cue. When the ball passes this electronic eye, two things happen. A relay switch tells the A2 to get busy, while a camera snaps a picture and sends the data to the scoreboard. The A2 locates the standing pins and snatches them up, while a sweeper clears the pin deck of fallen ones. The same pins are then set back down in the exact position the bowler left them in. Back in the pit area, the fallen pins separate from the ball. A belt sends the pins to the top of the machine, where they drop into a metal tray called a turnaround pan. The weight of the pin's body makes it drop heavy part first into the pan, so they always load right side up into the distributor wheel. Each time a pin loads, it triggers a clutch, which moves the carousel into the next position, ready to take the next pin. While all that's going on, the A2 gets the ball back to the bowler ASAP. The ball makes its way through here to an elevator. And from there, it rolls along a downslope tunnel as gravity sends it back to the player. At the end of the shaft, a series of motorized rollers send the ball up this S-shaped curve. It all happens in about the same time that it takes to tie your shoes. After the bowler takes his second and final shot of the frame, the sweeper clears any remaining pins. Sensors on the pin deck detect that there's no more standing wood. So, it sends a message to the distributor wheel to release the pins, all 10 of which are reset. The A2 automated pin setter machine completes its cycle like it has every day, every year, and every decade. Smoothly and efficiently. This old boy rarely keeps a bowler waiting. The desert sun, focused beyond the boiling point to make electricity. In this solar power plant, it's all done with mirrors. 3/4 of the known universe is hydrogen, but just a little in a fuel cell takes this ride a long way. Ever feel like you're just a small cog in a big machine? Well, hop on the escalator and join the crowd. 3,000 needle stabs a minute. If you're not cringing yet, wait till you meet the tattoo gun. Let's take the lid off these machines and see how they work. There are a lot of ways to harness the sun's power, like with a magnifying glass or a curved mirror, both of which can concentrate sunlight into intense heat. And that's exactly what inspired the creators of the Solar One to build a low-emission power plant out here in Nevada's Mojave Desert. Let's see how it works. In a desert where the sun shines 300 days a year, 200,000 mirrors side by side, row on row, form hundreds of parabolic troughs, reflecting sunlight with a surface area of about 50 football fields. That makes enough electricity to keep the power on in 14,000 homes year-round. So yeah, we're talking solar here. But not the pricey silicon cells that run our calculators. At this scale, that would cost a fortune. This is sunlight concentrated 70 times its normal strength, hot enough to burn your skin instantly. But here, it's focused on heating oil inside these tubes. And that hot oil is harnessed to boil water, which makes steam that drives a turbine, which makes electricity. Simple, right? Well, before you go out and build one, there are a few problems to overcome on a solar power plant like this. Number one, regular mirrors at home don't reflect nearly enough light to do the job. Two, your mirror has to move all day. The sun, that is the Earth, won't sit still. And finally, what do you do with a solar plant at night? Okay, first challenge, the mirrors. Household mirrors are fine for touch-ups, but are backed with a cheap spray-on coating that absorbs a lot of light. Pricey laboratory mirrors use silver coatings that reflect most of the light that hits them. And the ones here take it up another notch, reflecting almost 100% of the light that strikes them. To heat things up even more, they're curved. This concentrates the light onto the oil tubes that sit perfectly at their focal point. Focusing light is one thing. Putting it to work, another. So engineers clad the oil tubes in a special glass that intensifies the sun's rays even more. By the time the hot oil travels through nearly 20 kilometers of tubing, it's 4 times hotter than the boiling point of water. That's twice as hot as the oil used to make fries. The oil's now pumped into the guts of the plant and is ready to boil water. Oil tubes run down the center of these water pipes. The water absorbs heat from the oil, turns to steam, and heads straight to the machine's generating station. All of the electricity from this power plant is produced with conventional steam turbines. Steam drives the blades, which spin a generator which delivers electricity to the local grid. Once the steam has fueled the turbine blades, it cools down and loses its, well, steam. It's not hot enough to drive anything, but it's still vapor. It's got to cool down before it can be used again. So it heads to a rain room, where steam is trapped, condensed, and returned to the system. The second challenge for this machine is to follow the sun's arc. Sunflowers have to move all day in order to capture the sun's energy. If these mirrors were stuck in one place like a traditional solar panel, they would only reach their maximum potential for a few minutes a day. So, electric motors are placed within groups of mirrors that allow them to follow the sun's arc. On to the third challenge. What happens after sundown? No sun, no power. There are plans for thermal storage tanks filled with heat-trapping molten salts, but they're still on the drawing board. So at night, the Solar One switches to this natural gas burner to keep the turbine spinning. Good thing that demand for electricity peaks during the day. And that's when this machine delivers. And boy, does it deliver! 60 megawatts of power with almost no emissions, preventing 20,000 cars worth of CO2 from entering the atmosphere every year. The Solar One, a giant machine with a small footprint, capturing energy from the sun. It's no magic trick, but it is done with mirrors and no smoke. This motorcycle is powered by hydrogen, the simplest and most plentiful element in the known universe. Its creators called this bike ENVI, short for Emissions Neutral Vehicle, and you can make a cup of tea from the only thing that comes out of its exhaust. You guessed it, water. And what makes the ENVI go is this mini power plant called a fuel cell, which produces enough electricity to keep the bike rolling. Not bad for a machine that can hit 80 kilometers an hour. Okay, so it's not exactly a rocket, but it is fueled by rocket science. The first practical fuel cell system was developed by NASA in the early 60s to generate electricity in space capsules. A good way to understand fuel cells is to see how hydrogen is produced, and it's actually pretty simple. Fill a container with water and run an electric current through it. This splits hydrogen and oxygen from the water molecule, and the process is called electrolysis. This is the science behind producing hydrogen gas. Now, if you reverse that process and figure out how to rejoin hydrogen and oxygen, you'll create electrical energy along with water and a little heat. But it's not a fuel cell yet. You need to figure out how to harness its electrical energy. And to power this bike, it needs to be compact and portable. Here's how it works. These vents near the handlebars stream outside air to the fuel cell. The attraction between oxygen and hydrogen helps the fuel cell produce electricity. And that's all about electrons. Electricity is simply a flow of electrons. A fuel cell's primary function is to liberate them. Hydrogen enters the fuel cell on the left, oxygen on the right. A platinum film strips electrons, in yellow, from the hydrogen, leaving behind protons. Both are attracted to the oxygen on the other side, but electrons are stopped by this membrane. They now need to find their way back to the protons. The only way out is along wires to an electric motor that spins a drive belt and gear on the back wheel. After passing through the motor, the electrons find their way to the other side of the fuel cell. As they meet up with protons and oxygen, they form H2O, a chemical soup known as water. That's the only emission this fuel cell belches out. And save the jokes about this having a sewing machine engine, because this puppy could power 60 of them. Okay, the ENV is powered up. How do you keep it going? Simple. A fuel cell will go on forever, so long as it has a source of hydrogen. When the fuel cell runs out, all it needs is a fill-up. And there's a ready supply of it here, at Loughborough University in England, where this prototype was born. Filling up a fuel cell is as exciting as topping up the gas tank in your car. Minus the fumes. And unlike a conventional motorcycle, the only sound you'll hear from this machine is the rubber on the road. We're still a few years away from hydrogen-powered vehicles in the local parking lot. But when we get there, you may have your own personal fuel cell to power or charge just about anything, anywhere. And oh yeah, a motorbike too. This is the Great Cattle Drive. Day in, day out, over and over again. In some office somewhere, flow dynamics experts study our patterns to get us onto a machine that's basically a tricked-out set of stairs on a conveyor belt. So, how does it work? Escalators not only get us upstairs, they process crowds without damaging the goods. Today's escalator designers have 3 major challenges: keep it running smooth, quiet, and safe. Powering a busy escalator is like pulling a fully loaded SUV up a 30-degree hill. But under this machine, there's nothing but a puny 10-horsepower motor. How is that possible? Sure, it spins fast, but there's no way it can drive a fully loaded escalator. It was installed because it's whisper quiet. And that's important if you want people to use them in public spaces. Going with a larger direct drive motor would make way too much noise. So to generate enough power, this little guy needs a gearbox. The gearbox steps down the motor's RPM, and that translates into increased horsepower to the larger drive gear. And when you tow anything up a hill, power is always better than speed. But this is also a powerful, potentially deadly machine, and fatal accidents still occur around the world on a regular basis. Tumble into one of these, and you may as well fall into the jaws of a shark. And that's no joke. Escalator accidents kill more people per year than sharks. So when it comes to safety, designers look at every inch of the escalator, especially at the 2 trickiest parts of the ride: how you step on and off the machine. To make life easier, they came up with the level loading platform. This design feature remains flat for the first few steps as you walk on, and gives you a moment to adjust before the step beneath you rises. Some early escalator models force patrons to jump onto the first rising step. Not exactly the challenge you're looking for at a shopping mall. Each step has upper and lower wheels on its ends, which fit into 2 sets of tracks. The upper set of wheels join together to form parallel chains in a continuous loop. This chain of wheels fits into a cog of the main drive gear and into notches in the main drive wheel. The steps rise and stay level through the ride at 1 to 3 kilometers per hour, then collapse to let you off. While riding, you hang on to flexible handrails. They have their own rollers and their own path, but are driven by the same drive mechanism as the steps, so they stay perfectly in sync. Other welcome design features on this machine are the comb plate and the step grooves at the end of the run. They work together to keep loose shoelaces, debris, and curious little fingers from getting caught. And if the handrail ever goes out of sync, if anything gets jammed or slows it down, or if the impact sensors in the comb plate sense anything wrong, the brakes will bring everything to a safe stop. The Escalator first appeared as an amusement park ride in 1896. Today, they give over 90 billion rides a year in North America alone. And the only time we ever notice them is when they break down, and we haul ourselves and our assets all the way to the next floor. Tattoos have been around for thousands of years, and they've never been more popular. One in 8 American adults have at least one tattoo. That's 40 million people. Which is pretty crazy when you realize how much it hurts to get one. And well, they're kind of permanent. It's a mechanical rattlesnake that spits ink instead of venom. So how does this machine work? On the surface, tattoo machines are pretty basic. You can build one using a motor from a hairdryer or a vibrating toothbrush with guitar strings and erasers. And your ink can be taken from a simple ballpoint pen. Or you can sharpen a stick, put dye on the end, and poke holes in your skin. Just don't go trying any of this at home. All you have to do to make a tattoo is puncture the epidermis, or outer layer of skin, and deposit color into the dermis, or second layer of skin, about 1 millimeter below the surface. And this machine does it up to 50 times a second. Which means for every minute in the chair, you're getting stabbed 3,000 times. And if it takes up to 3 hours to create one, that's 540,000 punctures. Ouch. Then there's the problem of accuracy. You can't make detailed art like this without micro-precision. The tattoo machine controls needle depth, speed, and application to within a fraction of a millimeter. It hurts like a dental drill, sounds like a dental drill, and is as precise as a dental drill. It starts with a bunch of parts and one elastic, divided into 3 main sections: the base, the mechanism, and the needle. The business end is, of course, the needle. It's soldered to a metal arm that connects to the armature bar, the part that does all the work going up and down. A spring connects the armature bar to the base, the hunk of metal that looks like a rabbit ear with a screw in it. And the elastic? It keeps the hyper-fast needle from going off track. No coloring outside the lines here. The tattoo machine is armed with razor-sharp stainless steel, not tipped with a simple sewing machine needle. Modern tattoo needles come in a wide array of designs. They may look medieval, but are created to deal with some amazingly intricate and, well, special requests. The needles make tiny successive holes in the skin. Picture a sewing machine working through fabric. The ink is deposited into skin just like the thread that creates a stitch. The skin has to be stretched tight during the process. If left loose, the needles get stuck, the ink bleeds out, and makes a mess. Let's see how it works on a new design. It begins with an outline. In order to trace it, the machine is set up to draw a fine line. So, it's loaded with a needle that's round like the tip of a pencil. After the outline is complete, it's time for shading. So the machine needs a new set of teeth. Shading needles are configured like a comb. The more needles in a configuration, the more ink is transferred. The multiple needles create matching holes that are filled at the same time. The needles get up to speed by harnessing electromagnetism. And that's controlled by this power supply. A foot pedal turns the juice on and off. This drives the machine at rates of over 4,000 revolutions per minute. A sports car can hit 150 kilometers an hour at the same RPM. Power travels along cables to these coils and creates a magnetic field. This pulls down the armature bar and forces the needle into the skin. As soon as the armature bar hits the coils, it breaks the electrical circuit. The magnet turns off, and this spring snaps the bar back up. As soon as it hits this contact, the magnet is reactivated and the needle is driven down again. The rate of the needle in this machine is so fast, it matches the wing speed of a hummingbird. But birds' wings do not cause sharp, burning pain. In a world where everything is disposable, these works of art are for keeps. Whether for social prestige, spiritual devotion, tribal rite of passage, or a momentary lapse of reason, tattoos are the ultimate visual sacrifice for personal expression. This machine has taken an ancient art form and made it perfect with a little modern know-how. The rally car is fast, but speed isn't everything. This machine is built for trouble, from the ground up. And when you see a cuckoo this big, on a mechanical clock this tall, you gotta wonder what makes it, well, tick. The lift lock is a giant elevator that raises boats in a 2 million liter tub, all without gas or a motor. The web offset printer, high-speed printing at 20 kilometers per hour without a single smudge. Let's take a look inside these machines and see how they work. This is a rally car. It may not look like much sitting here, just a regular car with a few bells and whistles under the hood, right? Wrong. This machine may look like a Clark Kent, but once it's turned on, it's a supercar. The ride you pick up at the local dealer is related to the rally car, but we're talking distant cousins here. Really distant. In fact, the only thing that's left from your car on this machine are the lights. Turbocharger, big brakes, steering. It's all redesigned for speed, control, and handling. To beat an insanely difficult course without killing anybody. Let's see how it works. First, speed and control. Two things make that happen. The engine for acceleration, the brakes for taking corners and maintaining control. High-end rally car engines pump out over 300 horsepower. Thanks in large part to its turbocharger, which is basically a turbine placed in the car's exhaust. The turbine spins up to 150,000 RPM. 30 times faster than the engine. All that spinning powers a compressor that sucks in the air from outside, compresses it, and injects it into the engine's combustion chamber. More air means you can burn more fuel, with explosive results. And all that power shows up here at the start line, where it rockets the car up to 100 kilometers an hour in under 4 seconds. And that speed is great on the straightaways of a rally course. But these races are won and lost in the corners, where small mistakes cost valuable time. To master corners, this machine needs some serious stopping power. And it comes from some of the best brakes money can buy. Most cars have disc brakes with a single piston that move a brake pad onto a disc that slows the wheel. But they would literally disintegrate out here. A rally car needs as many as 8 to maintain speed and control. What about this challenge? A 180-degree hairpin turn. Top drivers make it look easy. A regular car and its driver? Not so much. Rally cars come equipped with a powerful handbrake that allows for this kind of action. You may use yours to park, but this machine's not built for standing still. Its lever sits next to the steering wheel, so the driver can grab it quickly. An independent hydraulic system locks the car's rear wheels, and around you go. Now that's what this machine is all about. It's also about staying in one piece. In a rally car, every seam gets a continuous weld, including the roll cage. This molds the body into a single unit, so on impact, the shock is evenly distributed. On top of that, the roll cage is structured with triangles directly to the frame. The cage is made of chromoly, an alloy that is lighter than steel and stronger too. The triangle design distributes force evenly, allowing it to withstand crushing blows from all directions. So not only does the rally car survive a rollover that would crush your average car, it recovers and keeps on going. The roll cage also provides a rock-solid base for the shock absorbers. Each has 2 key components: springs and dampers. They work together to absorb everything the road dishes out. The problem with springs is that they tend to expand as quickly as they contract, which makes for a very bouncy ride. The damper, a hydraulic chamber with a piston inside, controls the expansion and vibration of the springs, maintaining critical contact between the rubber and the road. Low and stiff for road races, high and loose for off-road. A set of 4 sets you back about 7,000 euros. But if you cheap out on the shocks, you'll pay a price out here. It's also all about staying on the road. The steering wheel is coated with a felt that locks in the driver's gloves like Velcro. You don't want to lose your grip out here. So rally cars are designed to keep control panels as close as possible to the driver. These paddles shift a gear in 50 milliseconds without the driver ever letting go of the wheel. And that's important because the difference between winning and losing a rally race is measured in fractions of seconds. When driver and machine get it done right, the champagne flows. If either slips up, the results are decidedly more painful. For speed, agility, and durability, nothing compares to a rally car. This machine may look like the one in the showroom, but don't go bringing your ride out here. This domain is reserved for the supercar. Welcome to Marienplatz Square in Munich, Germany. Home to a tower which houses one of the world's great mechanical timekeepers and a little number called the Glockenspiel. Its parts are spread out over 8 of this tower's 11 floors. Parts that include a bunch of these guys, a giant music box, a room full of gears, and 7 tons of bells. 100 years of gonging, cavorting, ticking, and talking. Let's see how it works. And let's start at the center of this machine with its amazing clock, which, like all big mechanical timepieces, is driven by a pendulum. Pendulums give us tick and tock, as well as the means to measure time accurately. But to do that, clockmakers have to overcome several stubborn challenges. The first is getting all of its parts to move at a precise unit of time that is repeatable, like 1 minute. So how do you get a minute hand to move precisely every 60 seconds? It starts with a little help from gravity, which gives the pendulum its perfect timing. You have to adjust its length until the swing lasts 1 second in each direction. That's it. The pendulum's weight doesn't matter. Gravity is constant. Neither does the distance it swings. All that matters is the length. And in order to work accurately, every pendulum is bolted to this, the escapement. As the pendulum swings past its center point, the escapement's teeth allow the gears to escape, one at a time. This creates a familiar sound we all know as tick. And as it swings back the other way, you guessed it, tock. Which leads us to a second challenge, how to beat friction that wants to stop the pendulum. After every tick and tock, the special shape of the teeth give the pendulum a very slight snap, which travels down its shaft. It's not much, but it's just enough for the pendulum to overcome friction and keep moving to the end of its swing. Oh, and if you're wondering about this small clock face here, it allows technicians to keep track of the time on the tower's giant clock. Imagine having to run down the tower and into the square to check it every day. Okay, so the seconds are ticking by perfectly. But how does that turn into this? A series of metal rods connect the mechanism to the clock. The muscle to move the giant hand comes from a hanging weight. Same idea as the one on your grandfather clock. When the weight falls, this cable turns gears, which turn the rods, which turn the hands. And that sets up the machine's third challenge. How does the escapement keep the whole thing from spinning out of control? It counts out the seconds, and after 60, lifts a release arm that's been stopping the weight from falling. The weight is released for a fraction of a second, just long enough to turn the gears that turn the hands. This repeats every minute. As the weight nears the end of its run, a small motor winds it back up to the top to start dropping all over again to power the clock. But there's one more challenge. In making timepieces this big, clockmakers created a problem. Bad weather pushes on its hands, which transfers back through the gear train. The heavy weight can resist the force, but can damage the escapement mechanism. So they installed a mainspring called a remontoire that drives the escapement, which powers the pendulum. When the weight falls, it rewinds the spring. This gives the escapement the power it needs while isolating it from brutal forces outside. So there you have it. This is what makes a giant tower clock tick and talk. All right, now let's check out the Glockenspiel. On level 9, a supersized version of your grandma's music box. It transforms individual notes from a song into electrical signals with these metal pins. Those signals control the gears on this table that yank long cables that in turn pull on clappers, clanging out classical tunes on 7 tons of bells. Each pin sends a note to each gear that plays a bell, and each bell plays its part. For these life-size figures on the 8th floor, which are driven by an electric motor and a set of gears. Jousting knights in one show, dancing barrel makers in another. And then a rooster pops out for good measure. It's a bit like an old cuckoo clock, only with more gears and bigger cuckoos. Floor show or not, it's the pendulum that counts on this machine. And you'll find it on every mechanical clock there is, cuckoo or not. This is the Peterborough lift lock, located an hour and a half north of Toronto, Canada. It's a pivotal linchpin of the Trent-Severn Canal, a 386-kilometer waterway that allows boaters to travel with ease between the Great Lakes. Built in 1904, it easily hauls 1,500 tons of water, equivalent to almost 1,300 passenger cars, from bottom to top in under 90 seconds. All without using a single watt of electricity. Okay, the control panel lamps are electric, but that's it. It's also the highest hydraulic lift lock in the world. Let's see how it works. Lift locks are built when a canal needs to get past a natural barrier, like a waterfall. That's where the lift part comes in. So, how do you do all that without motors or electricity? With help from gravity and water. This guy fires a piston beneath the lock to raise this gate on the bottom tub. This separates you from the canal. And that leads us to our first problem, lifting a giant tub. All it takes is water and gravity. The lift lock is like a seesaw. One side goes up, the other has to go down. But the top tub needs more weight to do that. An extra 30 centimeters of water flows in here. That makes it 144 tons heavier than the bottom tub. It uses water for weight because as far as this machine is concerned, you and your boat are weightless. As your boat floats, its total weight displaces its equal weight in water. So no matter how many boats are squeezed in, the weight never changes. Okay, so we're moving thanks to that extra sip of water in the top tub. But how exactly are we moving? What's preventing this 2 million liter bathtub from smashing straight down into the canal? 2 identical rams riding on a cushion of water. The rams move inside these cylinders called press wells. As the top tub descends, it drives the ram beneath it down. Water in the press well is then forced up this narrow space and channeled through a connecting pipe to the other side of the lift lock, where it forces the second ram and the tub on top of it up. When the ride is over, the guy upstairs shuts off a valve located in the center of the pipe that joins the two press wells. This locks the tubs in place, and you're free to fire up your boat and motor away. It may be old, but the engineers that built the Peterborough lift lock knew a thing or two about green technology. Water and gravity. Simple. A century on, still the highest hydraulic lift on record. Major daily newspapers in London, New York, or Paris have only a few hours to print over 1 million copies and get them on the street. And they couldn't do it without the web offset printer, a machine that prints non-stop from feeding to folding without a smudge. It's called a web offset because of the configuration of paper paths. For newspapers, it's the fastest and cheapest form of high-volume commercial printing. 11 kilometers of paper in just 40 minutes, changing the rolls on the fly without stopping. The paper runs through this printing stack at up to 10 pages per second. And these rollers are the key to the machine's ability to spit out such high-speed precision. Here's how it works. The actual printing plate is a flexible aluminum sheet that wraps around a drum. But on a closer look, that's a smooth surface. How does a printing plate make an impression with no raised edges? It's based on the fact that oil and water don't mix. A special coating on the aluminum plate is designed to absorb oil-based ink. So, if we ink this plate now as it is, it would produce solid black. So, ultraviolet light is used to project a 4-page digital image onto the plate's coating. The parts exposed to the UV light harden in place, while the unexposed parts of the coating dissolve away in a chemical bath. Emulsion and bare metal now form a printing plate. Once loaded on the print cylinder, the plate collects ink and water from rollers. The hardened sections of coating absorb ink. The other parts of the plate take on a film of water that keeps the non-printing areas ink-free. So, the ink-coated plate is ready to transfer, but not directly to paper. That would wear out the plate too quickly. The metal plate is wrapped around this drum. The ink image is offset from the plate to a rubber roller called a blanket, and the rubber then transfers it to paper. That's why it's called offset printing. Now, to print both sides, the paper is sandwiched between an opposing set of plates and rollers. With a 4-page printing plate on each side, one turn of the drum produces 8 pages in 1/10 of a second. It's all black and white. But what about photographs? How does this machine print gray? Well, it can't. But here's how it works. A photo is filtered through a screen, and the gray tones are broken down into black dots called halftone. The closer together the dots, the darker the effect. Pull back, and the halftone image appears as gray. We make up color the same way. When you mix black and 3 primary colors, cyan, magenta, and yellow, you can create every color that exists. The original color image is split into 4 halftone plates. 3 plates carry one of our colors, and the 4th carries black. The color inks are loaded into the machine. Then, the plates are printed one after the other with halftone dots. And as long as they are perfectly lined up, our perception once again connects the dots into a continuous tone. This press has 6 printing stacks. The tall stacks have 4 sets of drums so they can print in full color, and the smaller ones just print black. The web of paper feeds through the stacks from both ends and meet at the collator. The machine collates, folds, and chops the newspaper, then sends it along to be stacked and bundled at over 500 copies a minute. The web offset printer set the standard for hot off the presses. Even in today's digital age, nothing can beat this machine for volume, speed, and cost. A 50-story Ferris wheel so finely tuned that stopping would throw it off balance. Let's jump on and off the London Eye. You practically wear this jet ski. It's a radical rethink in watercraft design that lets beginners ride like pros. 4 times higher than Niagara Falls. A man-made lake, lots of power. Hoover Dam beyond the postcards. Red, green, and amber. The modern traffic light controls our movement. Let's look inside these machines and see how they work. This is the London Eye, the largest cantilevered Ferris wheel in the world. Ferris wheels are nothing new. They've been around since 1893. And none of them ever veered from the basic bicycle wheel design until the Eye came around. This big wheel is different. It's held up from one side, and while at work, it never stops moving. The Eye's designers had some complex challenges getting it off the ground, then getting it running. London's always been a big draw for tourists, but it's never been known for its skyscrapers. A bird's eye view here was always, well, for the birds. So, for the new millennium, London leaders held a design contest to create a top-of-the-world view. There were 3 conditions. Be reasonably priced, keep the footprint small, and make it easy to disassemble. That's because they planned to take it down in 5 years. But the Eye was so popular, they kept it as a permanent fixture of the London skyline. The first challenge was just getting the wheel to the building site. The River Thames has 2 problems: 6-meter tides and a lot of obstacles. Easy enough for small river traffic, but getting large bits of the wheel through narrow passages like the Thames flood barrier and numerous bridges meant perfect timing with changing water levels. The tightest squeeze they faced had a clearance of less than ½ a meter. Getting it here through an obstacle course was one challenge. But nothing like the second problem, getting it up. In construction terms, this site at Jubilee Gardens is a postage stamp. Not nearly enough land to assemble 1,700 tons of metal. All they had was the river. They placed the Eye's pieces on 8 temporary islands, where they were put together. Then, the wheel was pulled up to a 65-degree angle. After some adjustments, it was swung into its final position. These cable backstays anchor the Eye into 33 meters of concrete. So, it's up and it's secure. How does it keep smooth and stable while carrying up to 800 passengers at a time? For that, we need to look to the eye's pods and some pretty special truck tires. 32 glass pods attached to the eye's outer rim. Each holds 25 riders and weighs 10 tons. That's a lot of weight hanging off the edge of a wheel. And these pods don't swing back and forth like the seats on a typical Ferris wheel. The eye's pods each have a built-in leveling system to stay horizontal. There are 2 bearing rings for each pod. The inner part of each ring is fixed to the wheel structure. The outer part is fixed to the pod. So as the wheel turns in one direction, the pods rotate the other way to maintain their horizon. Each pod turns on these circular mounting rings, while the leveling system keeps everything running smoothly. Each rotation takes 30 minutes. Each pod traveling just under 1 kilometer per hour, 6 times slower than a casual stroll. That lets passengers step on and off without the wheel ever having to stop. And it gives you a lot of time for these great views. This spindle at the eye's center holds the whole thing together. 23 meters in height, together with the hub, weighs over 300 tons. 64 spokes stabilize the machine, along with 16 rotation cables. These attach to the hub at an angle, preventing lag in the eye's rotation. The wheel itself is turned by this set of truck tires. Hydraulic motors turn the tires, and the rotation of the tires turn the wheel. If you're up the eye in bad weather, these dampers fixed around the rim prevent vibration caused by high winds. That could weaken and wobble the entire structure. Not quite the ride that sightseers line up for. They buy their tickets to get an unparalleled view of one of the world's great cities on a machine that delivers exactly that. An elevator, observation deck, and great ride all in one. Almost 50 stories high in a city shy of skyscrapers. The only view of London worth the ticket. There are 3 basic classes of jet ski. There's the familiar sit-down model. Big, solid, great for cruising. The sporty stand-up model, designed for extreme tricks, but not something you master on vacation. Then there's this guy. A prototype called the Samba. Inspired by race bikes, it's one of the fastest jet skis on water, with radical features that lets a beginner ride like a pro. Let's see how it works. To make a jet ski maneuver like this without trashing its driver, you gotta respect the laws of hydrodynamics. That's why the Samba is built super light, only 90 kilograms, so it gets up to speed in a heartbeat. This other beast weighs over 3 times more and has to push a lot more water out of the way getting up to speed. Add a top-of-the-line custom engine to the Samba, and you've got a machine with a crazy power-to-weight ratio advantage. To see what powers a jet ski, take a look at this rocket, demonstrating that every action has an equal and opposite reaction. And all jet skis are water rockets. Push a stream of water one way, the machine goes the other. Its powerful water jet is driven by an impeller, which is pretty much a propeller jammed into a tube. Impellers take water in through a wide opening and force it out through a smaller one. This creates what's called a Venturi effect, where low-pressure water behind the impeller pulls more water towards the blades, increasing its speed. And when moving, extra water is rammed into the housing through a scoop, maximizing the jet effect. At its top speed, the Samba spits out enough water to fill your bathtub in half a second. The impeller is powered directly by the engine. That's fueled with a custom mix of high-octane gasoline and nitrous. Every bit helps. But after several years and a few blown engines, Samba's designers discovered that speed wasn't just about engine power. It's about how the machine contacts water. So, they came up with a radical new hull shape for a smoother, lower friction ride, and allows them to easily hit speeds over 60 miles per hour. All right, it's skinny and fast, but a low-friction ultralight body and a powerful engine are one thing. Controlling them, another. The designers wanted much tighter handling than other machines. All jet skis turn the same way. The steering works by changing the direction of the water jet from side to side. But it's not enough to get you doing this. Or this. Leaning on one of these won't do much. This machine outweighs the driver 4-to-1. But the Samba weighs about the same as its rider. So you change its angle of attack with a simple body lean. A light frame and low driver position perfectly positions the machine's center of gravity. The driver's race bike crouch looks cool and aerodynamic. But in terms of handling, it allows instant communication between body and machine. In this position, the driver's center of gravity is the area framed between his shoulders, hips, knees, and extended wrists. And this sweet spot gives you maximum control over the machine for tricks and turns. But even the perfect weight ratio and a low center of gravity won't make it easy to do spins like this. With its new hull, the Samba's been overcoming friction for maximum speed. Now, to spin some real tricks, it wants all that friction back. And it does it with these wings that stay out of the water until you lean into them. Then they catch. This creates so much friction, it turns the water into a fixed point around which the machine rotates. It's a bit like pitching a pole into the ground and spinning around it. A natural move for the next generation of jet skis. Just don't take it too far. Or on second thought, go ahead. You don't need to be a pro to rock this machine. A low-slung driver position, radical hull design with lots of speed and control. Which is why you may see a lot more of this machine on the water. If you see it at all. Water provides 1/5 of the world's electrical power. And it's done with some of the largest machines ever built. Hydroelectric dams. Let's check out a famous one, Nevada's Hoover Dam, and see how it works. A machine like this blocks a river to form a deep reservoir that creates water pressure to drive turbines that produce electricity. Sounds simple enough, but the challenges facing dam builders are enormous. First, how do you block a river that doesn't want to stop moving? With a lot of concrete. In the 1930s, It took 5 million barrels of cement and 2 years of pouring to build this retaining wall. Pressure from all that blocked river water is so immense, they built the wall's base over 2 football fields wide to hold it back. And it's not a single block of concrete either. Because as concrete dries or cures, it gives off heat. This much concrete poured in a single block would have produced so much heat that it would have taken over a century to set. So, the wall is actually a series of individual blocks that cooled one at a time after they were poured. They were locked together with notches, like pieces of Lego, and then glued with a thin cement mix. With a concrete wall over 4 times the height of Niagara Falls. Only one major feature makes it strong enough to hold back the Colorado River. The dam's shape. See how it's curved? It's built in the form of an arch, which spreads the force of the water evenly toward the solid canyon walls. No weak spots. There's enough water pressure in Lake Mead to literally impact the Earth's crust. The canyons behind the dam hadn't felt anything heavier than air for a long time. So as the reservoir filled up, its weight in water caused hundreds of small earthquakes. The first time, unsuspecting geologists understood that man-made reservoirs can impact the Earth's surface. The next challenge for the hydroelectric dam is to harness enough water pressure to produce electricity for 500,000 homes in California, Nevada, and Arizona. Not bad for a machine that doesn't spit out a single puff of smoke. What it does spit out is water pressure, the key to this machine's output. Sure, running water can create power, but not nearly as much as water under pressure. Think about washing dirt off your car. Which would you rather use? We thought so. And Hoover's turbines need the same thing. So, the dam takes water from its reservoir through 4 intake towers, down 9-meter-wide pipes to the machine's turbines, located almost 50 stories beneath Mead's surface. Water is pulled down by the force of gravity. As it descends, the water pressure increases. The deeper you go, the stronger the pressure. And down here, the pressure is bone-crushing. More than 100,000 kilograms per square meter. That's like compressing 2 elephants into a shoebox. The pressurized water flows from the intake tunnels into these tapered pipes. The tapering effect creates a water jet that blasts into Hoover's turbines. But to manage the machine's electrical output, the water has to be controlled. These wicket gates open and close to change the amount of water spinning the turbines. There's enough water rushing through here to fill 15 swimming pools in 1 second. Okay, the turbines are spinning. What now? How does all this add up to electricity? A shaft connects each turbine with a generator, which houses a whirling assembly of electromagnets spinning next to a ring of copper coils. The swirling magnetic field literally pushes the metal coil's electrons around, and that's what creates electrical current. Hoover's got 17 turbine generator combos that send all that electricity out to an array of transformers, which then send it out to the grid and to all its customers. When it was finished, it was the largest concrete project in the world. Tourists may flock here to marvel at its size and beauty. We come to see how simple it really is. Block water, pour it down a man-made hole, spin some turbines, make power. Nothing to it. Red, amber, and green. It's a language the whole world gets. There are subtle differences in signals from country to country, but their function is the same. The modern traffic light studies, predicts, and controls our movement. Large cities deal with millions of cars every day. Drivers may feel like they lose a lot of time waiting for lights to change, but traffic lights are meant to keep us organized as we move. Let's see how they work. The problem with city traffic is that it's never the same. At many big city intersections, you'll see a traffic control cabinet. It's a watchdog that keeps tabs on the traffic flow of its intersection. And it often gets the information it needs from here. Buried just beneath the pavement, a metal sensor keeps track of cars as they pass overhead and sends the data back to the control box that adds it all up. A program then adjusts the timing of the lights according to its car count. The control box information makes it back to here, a command center, where info comes in from all kinds of places. The pavement sensors, traffic cameras, 911 calls, road crews, traffic reporters, and of course, the police. All this input helps operators change the timing of traffic lights on the fly. When they're not doing that, they study simulators to help predict traffic flow at an intersection, and then reprogram the lights according to the results. These boxes also come with a program called a conflict manager. It makes sure that no one gets hurt from mixed signals. If anything falls out of sync, the box defaults the intersection to a single color. Speaking of color, let's see how the lights work. Halogen bulbs illuminate most traffic lights, but LEDs are taking over. They're brighter, which means safer. They last for years, which means low maintenance. And they save power, up to 80%. The light-emitting diodes in an LED lamp are laid out in patterns. They allow for faster switching and can even contain different color displays and patterns in a single lamp. In a growing number of cities, traffic light control systems also play a crucial role in getting emergency vehicles through traffic, with help from a remote device that changes lights on the fly. Don't we wish we all had one of these? It's a remote control light changer. It's called an Emergency Vehicle Preemption System, or EVP. And it changes traffic signals to clear intersections for emergency vehicles. Devices flash secret-coded infrared or light signals to a receiver that can detect an EVP from up to 900 meters away. Once the pulse has been received, the lights change as needed. This reduces response time for emergency vehicles and makes intersections a lot safer for other vehicles in the area. So, the next time you're waiting for a red light to change and you feel like you're just another number, relax. The box on the corner may just reward you with a string of green ones down the road. Ever look really closely at the fabric on your sleeve? See the pattern, the weave, and the texture. The high-speed loom does it all. Look over your shoulder. A silent spy may be tracking you. The micro drone has moved up from amateur to professional. It's a monster lumberjack. Grab, slice, and stack a bunch at a time. Meet the Feller Buncher. A low-level rescue flight over water, rocks, and land. Speed, turn, stop on command. It's the sports car of hovercrafts. Let's look inside these machines and see how they work. Weaving has been around since the early Stone Age. The basic concept hasn't changed, but speed and sophistication sure have. To keep us all in clothes and bed sheets, we need millions of kilometers of fabric every year. Impossible without the industrial loom. High-speed machines all over the world, like these outside Leeds, England, produce just about anything we need and want. Let's see how they work. First up, the basics. Take 2 sets of threads. The first is called the warp, 2 rows stretched lengthwise. The second set is called the weft, and it goes back and forth between the warp. Every time it goes through, the warp moves to trap the weft. The threads are now becoming a piece of fabric. To keep it from unraveling, a reed pushes the threads together. And then, the whole process starts again. To mass produce a wide range of fabrics, you need to organize thousands of different threads. So, the loom needs a lot of control. And it gets it from these devices called heddles. Each one has an eye through which individual warps are threaded. This gives the machine control of thread movement. Heddles are suspended on the loom's shafts, located here. When a shaft is raised, the heddles go up and the threads with them. To create simple patterns on one of these, you need a few hundred heddles and 2 shafts moving up and down together. Industrial looms have thousands of heddles and up to 24 shafts, all moving independently. That takes care of control. Now let's see how speed works on this machine. To manufacture massive amounts of fabric in a cost-effective manner, the loom needs to rocket the weft through the warp. Old-style looms use a shuttle, a spool of thread that unravels as it moves manually back and forth. Reliable, but slow and in constant need of reloads. This presents 2 challenges for the modern loom: how to weave thread quickly without a shuttle and spool, and how to minimize thread reloading. Enter the rapiers, one of the latest shuttle replacements. One rapier picks up a piece of thread, pulls it to the middle of the warp, and hands it off to its partner. It pulls the thread the rest of the way, while the first goes back for another strand. And because spools no longer have to travel back and forth, the rapiers draw thread from large bobbins. That means a lot fewer pauses for reloading, and this dramatically improves the machine's productivity. On the industrial loom, this handoff happens over 1,000 times a minute. This speed puts tremendous strain on thread snatched off bobbins at up to 250 kilometers per hour. If it breaks, the machine shuts down, and that costs money. So experts came up with a pre-winder, a device that preps thread for the rapier. It's a buffer that eliminates thread-breaking tension on the machine. Another side effect of speed is fabric dust. And to protect workers, it's got to go. Ceiling-mounted vacuums suck up the entire volume of air from the shop every 2 minutes. Okay, the loom is lightning fast, but how does it create different patterns and textures? A geometric pattern, like this plaid, starts with loading the warp with rows of different colored thread. Send a dark thread through the colored rows, you get this. Send a light thread across, you get this. The trick is switching between colors on the fly And for that, it needs a weft presenter, a component that selects different colors from bobbins and hands them off to the rapiers while they work. For complex patterns, a loom with a jacquard attachment is required. It's a mechanical wonder. The jacquard device controls all the threads loaded into the machine. Instead of ganging them together onto the shafts of a standard loom, every strand has its own control system. So, with a jacquard attachment, operators can control the paths of each thread into ornate designs. Instructions are sent to each individual thread as it races through thousands of weaves. All those tiny decisions add up to a pattern, kind of like how a bunch of pixels become a picture. Its namesake, Joseph Marie Jacquard, invented the first of these mechanical marvels in 1801. Until then, this kind of work had to be done by hand and was extremely expensive. His machine used punch cards to control individual threads, and some consider it the first computer ever built. Which is exactly how its modern descendant works, only electronically. Designs and patterns are programmed into the machine, and away it goes. The threading of a jacquard loom is so labor-intensive, it's usually done just once. When it's time to change colors, new threads are tied on to the existing ones. Even for a small loom with only a few thousand ends, the process can take days. Without these fabric workhorses, the cost of a single suit would leave most of us in last year's deerskin. The loom's a machine to be thankful for. It literally puts the clothes on your back. This is a hovering, unmanned aerial vehicle. The micro-drone MD4-200. Drones like this one are used for jobs like aerial mapping, fire inspection, law enforcement, surveillance, and search and rescue. Weighing less than a kilogram, its onboard camera records from a height of 150 meters. It's an eye in the sky that saves money and lives. Let's see how it works. The MD4 flies with the help of 4 fixed-wing rotors, each attached to an electric motor. You start it up, spin the blades, and up it goes. The design challenge is to keep the craft super light and whisper quiet, airborne and stable, all while transporting an HD camera. And to avoid losing it, program it to come home on its own when low on power, and land safely. When you tip the scales at less than a kilo, you don't need a big engine. That means less energy to fly and hardly any noise. To keep it light, designers chose carbon fiber for the MD4's body. A material born in the lab, made up of thin threads of carbon atoms in a hexagonal pattern. Weave it into fabric, create lightweight material with tons of strength. Small servo motors give the machine lift. All electric, without gears, the servos have more than enough power to fly the MD4. The 4-rotor platform keeps a horizontal and stable base in balance for taking pictures. That's the good news. But flying a quad rotor isn't like working a plane or a helicopter. 4 rotors means 4 sources of thrust, each needing constant adjustment. The motors are independently controlled by microprocessors that send and receive hundreds of signals to onboard sensors. The operator talks with the drone through a controller, sending FM radio signals that the MD4 converts into movement. To get a rock-steady hover, 2 rotors spin in one direction, the other 2 in the opposite. The 2 sets of rotors cancel each other out and keep the machine in a static position. If you drop the speed of one pair of rotors, the torque of the other 2 force the drone to spin. For a straight run, drop the speed of one rotor, which causes the leading edge to dip. Then you bump up power on the back rotor, and away you go. The machine gets all its power from a small rechargeable lithium battery, enough juice to keep it working for about 30 minutes. If the battery runs low during flight, sensors give the drone a pre-programmed flight plan to land it safely close to the operator, who just pops in a new one and sends it up again. And if the MD-4 loses radio contact, onboard GPS puts the drone in park to wait for its master. If it doesn't pick up a signal in 30 seconds, it makes an emergency landing automatically. The GPS also allows a user to switch to autopilot for flying the machine on a predetermined route. These firefighters in Birmingham, England, use the MD-4 to find deadly hotspots. Cops and security patrols sneak up on bad guys. And it inspects hard-to-get places for hydro crews. Flying around in silence with the latest cameras. It's a stable, floating platform for taking pictures, thanks to the quadcopter design that keeps the shot steady for as long as the batteries allow. If you're a softwood tree, between the ages of 50 and 80, live on a farm, and this machine shows up on your doorstep, you're in for a bad day. This is a feller buncher, a machine that revolutionized the lumber industry. And chances are, it cut down the wood that built your house and made your morning paper. It does the work of dozens of men, cutting up to 4,000 trees in a single day. One of these machines can clear about 100 football fields worth of trees in a week. All with the flick of a joystick. Let's see how it works. The feller buncher has 2 simple jobs: felling and bunching. Cut trees with a big saw, pick them up with a long, powerful arm, and set them down gently. First up, the blade. The feller uses a high-speed disc saw with indents to carry away wood chips, and teeth that are wider than the disc. If disc and teeth were the same width, pressure from the tree would sandwich the blade and the whole thing would grind to a halt. The teeth are made from carbide, a super strong alloy. Strong enough to rip through a ½ meter of dense, resin-soaked trees. The teeth cut through fibers inside the tree with these points. Then, rip out the weak middle section. As the tree is cut, it slides onto this holding plate. Without it, the tree's weight would freeze the disc and burn out its motor. Another great advantage of this machine is how low to the ground it can cut. Leaving behind big stumps wastes a lot of wood. And cutting low is more about reach than bite. Which brings us to the bunching part of this machine and its powerful hydraulic boom. The feller buncher needs distance from the trees to give its operator a clear view for a level cut, and to keep him and the machine out of harm's way. For that, you need a hydraulic arm that's strong enough to pick up and set down a 5-ton tree from 8 meters away. The hydraulic arm has 2 sections, the stick boom and the main boom. Getting these to work together is the key to success out here. With a single joystick, the operator moves and adjusts the boom's 2 sections to land in the right spot and make the perfect cut. Okay, you're through the tree. Why not just yell, "Timber, let it go"? Falling trees damage other trees. They're extremely dangerous. And out here, to be efficient, you need the wood out of the way. And neatly stacked for transport. To do all that, you need the hydraulic boom and its claws to be powerful, and you need a body that's not going to tip over. This machine's strong enough to grab several trees at once. After cutting, the operator closes the accumulator and hangs on while opening these clamp arms. When a second tree is cut, the accumulator arms are sandwiched between the two. A double-hinged joint allows it to slip free and grab the harvest, while the claw is free to grab the next tree. Meanwhile, these special ends, called snouts, keep the blade from accidentally picking up forest debris and sending it flying off in all directions. As the claw grabs, the machine stabilizes itself. It floats on a leveling system that allows the machine to bob and weave on a series of hydraulic cylinders. It's kind of wrestling with the tree as it picks it up and sets it down. With a pivot point near the cab, most of the weight is back here. A great counterbalance to keep the whole operation upright. This self-leveling machine operates on slopes up to 45 degrees. Handy when you're working the side of a mountain. Its tracks provide a great grip without wrecking the forest floor. So tree farms like this one can be replanted. The machine's 31 tons are evenly distributed over 6.5 square meters. At any point, its heaviest impact is less than 5 kilograms per square centimeter. That's less than the pressure you put on the ground as you walk. When the feller buncher arrived on the logging scene in the 70s, it changed the industry forever. The old-style lumberjack is a dinosaur now, and a machine that looks like one replaced him. You're flying over rocks, river currents, and land without a hitch. It's what hovercrafts do. The HoverTech Rescue Craft is an emergency vehicle working some rough waters in Canada's Fraser Valley. When a call comes in, it's got to unload fast and launch in seconds from almost anywhere. Designers gave this machine just one fan and one motor. And that's a hovercraft rule breaker. A traditional hover has separate fans and motors, one for lift, one for thrust. To keep it compact and light, this machine's single engine does both. Here's how it works. When you start up, the fan blows air into an airbag or skirt made from heavy-duty nylon. Air pressure builds up to the point it has to escape, and the only way out is to push the whole thing up and blast out under the skirt's pockets. You're up and floating on a cushion of air. But you can't go forward on lift alone. At this moment, other hovercrafts need a second fan to move forward. That's because they don't have this, a splitter that divides the fan's air, directing enough downward for lift, while sending the rest out the back for thrust. When you're riding on air, there's not much friction. So all this machine needs is a 65 horsepower engine to hit a top speed of 70 kilometers per hour. You can go just as fast on a boat like this, but you have to push water out of the way and burn a lot more gas doing it. With a hover, you're more aircraft than boat. No current or tide can touch you. Transitioning onto land is no problem. The flexible skirt, made of individual air pockets, moves up and down with the terrain. And if one of its pockets rips, the one beside it fills the gap. And if that one rips, replacement happens fast, like everything else on this machine. For steering, the handlebars are wired to rudders. Navigating obstacles is no problem, and allows the hover tech to reach an emergency fast. But what if it needs to slow down and just, well, hover? A traditional hovercraft can shut its thruster fan and float on its lift fans, but with just one, it's kind of tricky. Kill that fan at full speed, you lose thrust, lift, and slam into the water. Here's the workaround. And it's an idea borrowed from reverse thrusters in fighter jets. These buckets swivel into the blasting air and redirect it forward. Reverse thrust. So no loss of lift or control. The buckets provide pinpoint control when approaching a target. Once in position, killing the fan lowers the deck closer to water. A high-density foam shell keeps it floating while this guy climbs aboard. When it's time to go, adjust the buckets to balance thrust while the fan gets up to full power. Then spin the buckets and away you go. Designers broke a few rules making this hovercraft portable and fast enough for search and rescue work. Pretty handy for guys on call 24/7. Part boat, part plane, the HoverTech gets to the scene fast in a business where every second counts. An average aircraft would disintegrate doing maneuvers like a barrel roll or cartwheel. But the Sukhoi stunt plane can do that and more. This machine outturns, outpushes, and outworks ocean liners 1,000 times its size. If you've got a big ship that needs parking, then you need a tugboat. Some love the carousel. Others fear it, maybe for a good reason. Hanging on a single pole, this ride is a 10-ton balancing act. Let's open up these machines and see how they work. Born in the Soviet Union in the 1980s, the Sukhoi Su-26M is still the most sought-after stunt plane in the world. The 2.6 hits 450 kilometers an hour, does a 360 barrel roll in under 1 second, can hang in place, and takes more G-force than an F-16 fighter. It's built to sail through conditions that no regular plane could survive. Let's see how it works. To get a plane off the ground, you need two things: propulsion and wings. Engines, either jet or propeller, provide the motion, which increases airflow over the wings. And the wings provide the lift. The shape of the wings combined with fast-moving air produces downwash and reduced air pressure on the wing's top surface. These aerodynamic forces produce lift. The amount of air diverted depends on the angle of the wing. This is known as the angle of attack. At takeoff, pilots adjust the wings to increase their angle of attack and get the machine airborne. Now that it's up, designers had to figure out how to keep it there while allowing it to perform incredible stunts. There are 3 basic challenges. First, extreme angles like these will either crash a regular plane or tear off its wings. The shape and construction of the wings is critical to overcoming the violent forces of these transitions. Second, the controls on this plane are surprisingly basic. No electronics, no power assist. Hydraulic systems can fail under extreme loads, so how does a pilot manage without them? And third, all this engineering is meaningless if you can't keep the pilot alive. First challenge, keep the machine in one piece. The key to that begins with the stunt plane's wings. This is the profile of a regular aircraft wing. It's got a curved top and a flat bottom. This shape works great for lift, but good luck trying to fly upside down. If you tried to fly at this angle, you'd be heading in the wrong direction. Stunt plane wings are heavily curved and more or less symmetrical, so lift remains the same upside down or right side up. Another force working against flight is aerodynamic drag. The only way to perform tricks like this is to increase it. Create too much, you stall, and then you drop like a stone. So, stunt planes need low-drag wings, heavy-duty construction, and powerful engines to keep them from shutting down when they're upside down, sideways, and all twisted up. But what keeps it from falling apart? On this machine, the wings are covered in titanium reinforced with Kevlar, almost impossible to bend. These ultra-stiff wings transmit extreme forces onto the plane's spar, the main supporting structure of a wing. It's anchored to the fuselage at the plane's center and evenly spreads out stresses working against the wings. It kind of works like a seesaw. The forces on each side of the spar cancel each other out. All modern planes have spars, and they're all strong. But the 2.6s are made from solid graphite and can withstand forces of over 35 Gs. On to the second challenge, controlling the machine. From down here, airshow stunts may look like they're computer-controlled, but inside the 2.6, there's nothing but a stick and a couple of pedals to control the plane's movement. The stick is connected to elevators. Pull back, and they go up. That forces the tail wing to drop and the plane's nose to rise. This changes the wing's angle of attack, creating more drag and lift. Foot pedals control a rudder that moves from side to side for turning. The stick also connects to ailerons located on the wings. Ailerons help normal aircraft bank. They always move opposite to each other. One goes down, the other goes up. This increases lift on one wing and drops the other, allowing the plane to turn. In the 2.6, a sideways push on the stick engages the ailerons. Not that different from other planes, but they can't take it to these extremes. This machine's wings allow it to take a bank into a barrel roll, and a lift becomes a loop. And there's more. A sharp turn of the rudder with the push on the elevators turns a barrel roll into a crazy tumble. The machine really can do just about anything the pilot dreams up. And what the pilot can physically overcome. There's no power assist in the controls of the 2.6. Its builders didn't trust hydraulics or electronics on extreme moves, so they didn't install any. But they did give pilots a little bit of help with some clever add-ons. At the plane's tail, the front edge of the elevators flare out into these edges called horns, a kind of aerial power steering system. Watch how they help the 2.6 pull out of this dive. When the pilot pulls hard on the stick, it raises the elevators, but that's not enough power. At certain speeds and angles, where strength alone would fail, the horns help push the elevators the extra little bit, giving the pilot just enough control to keep the machine airborne. With its wing design, super strong construction, and a couple of engineering tricks, the 2.6 throws the aeronautical rulebook out the window. But there are other physical laws you can't throw out, no matter how special the machine. And that brings up the third challenge: gravity. Moves like these come at a price. The faster you change speed or direction, the more G-force you create. The resistance you feel as your body catches up to the plane is G-force. So, the next design challenge for the 2.6: protect the pilot during intense moves. On steep climbs, blood drains down the body and oxygen to the brain gets cut off. First, you go blind. Then you pass out. When diving, too much blood rushes to the brain. Eyes fill up, and you literally see red. The amount of G-force is directly related to the pilot's alignment with the machine's acceleration. So, the designers angled the 2.6's seat at 35 degrees. By reducing the direct line to G-force, the amount of blood that gets pushed around is reduced. Another line of defense for this nearly indestructible machine. But this Soviet icon also had to overcome some ice-cold problems. Find a proven, high-powered, lightweight engine that won't freeze up in winter, and then figure out how to start that engine on a frigid Siberian morning without a battery. To start with, build up a 360 horsepower radial engine with World War II pedigree that has 9 pistons arranged in a circular pattern. Just like the pistons in your car, these work in 4 strokes. They pull in air and gas with the first stroke, compress it with the second, ignite it with the third, push it out with the fourth. But firing in a circle sequence is trickier than a conventional inline engine. Watch them fire. First, every second piston goes off. The next time, those same pistons are skipped over while they expel the exhaust and suck fuel for their subsequent firing. Fighter pilots love this engine. Even if a piston or two got shot out, you still had enough to get home. Everything on this plane is manually controlled. No hydraulics to leak, no electronics to break down. The air-cooled engine even has a manual thermostat. The pilot opens and closes metal shutters like the aperture of a camera to adjust the engine's temperature. The Soviets had found their perfect engine: tough, dependable, and powerful for its size. Next, the battery, critical for turning over most combustion engines. But they needed to start these things in winter, and new batteries would drain in the cold. So designers came up with a surefire solution: air pressure. This ball contains compressed air that's injected into the cylinders to move the pistons, and that starts the engine. Once it's turned over, fuel smoothly replaces the air. There is a small battery attached to the engine, which showers the combustion chambers with sparks to ignite the air-fuel mixture. Smart, no-frill mechanical ingenuity. And here's another one: visual guides attached to the wings. These help pilots orient the machine flying upside down or coming out of a spin by lining up the guide with the horizon. And the horizon is the only thing that's ever limited this machine. Whether hanging from its propeller helicopter style or taking an earthbound dive, it's all about the performance. As for the airshow smoke, a high-speed pump injects paraffin oil into the hottest part of the exhaust pipe. The oil has a high flash point, so it doesn't go up in flames, but the pipe is hot enough to make it smoke. That may be the flashiest feature in a bare-bones, no-nonsense, unbreakable aerial hot rod that has dominated skies both east and west for over 2 decades. These are the sheepdogs of the marine world. Without harbor tugboats, megaships could never get into port. And we'd run out of oil, food, and pretty much everything else in a matter of days. As the size of ships have increased, so have the demands put on tugs. Conventional harbor tugs working here in Vancouver need all the help they can get. And it comes from this tractor tug, the newest and toughest member of the family. A sumo wrestler and dancer all in one that can push and turn a Leviathan 1,000 times its size. Let's see how it works. Tugboats need two things to get their job started: a big, powerful engine and a special hull design that allows them to dig into the water. Essential to help monsters like these parallel park. These harbor tugs pack around 1,800 horsepower. This tractor tug is driven by two 3,000 horsepower diesel engines. Precision-tuned with computer-monitored fuel injection and turbochargers, each one of these engines could power a full-size locomotive. But a locomotive has a huge advantage over a tug. It's got wheels that are always in contact with solid steel rails. Friction between the wheels and the rails make it easy to generate traction. Tugboats have to do it on water, which is always moving and, well, kind of slippery. All the horsepower in the world means nothing if you can't somehow get a grip and create leverage. The secret to winning that battle is in the hull. Tugs are kind of like icebergs. A big part of them live underwater. They ride low under the enormous weight of their engines, and as they power up, they sink even further. That's because they're built with something called a heavy displacement hull. Instead of riding on top of the water, it sinks into the trough of its own wake. More contact with the water means more friction and more pushing power. But to guide ships in and out of narrow harbor entrances, modern tugs need a lot more than power and grip, including independently controlled props, keels that go on the front of the boat, and indestructible winches. There's another kind of friction the tug needs. The kind that keeps you glued to the wall of a ship. And whether you're an old tug or brand new, there's no substitute for rubber tires. Even with all that friction and horsepower, these machines often work in teams. They have to on this big fella that's all loaded up and ready to head back to sea. The tugs take aim at clearly marked sweet spots and quickly push the freighter into a shipping lane. That's the work of a basic harbor tug. Heavy displacement hull, big engine, lots of tires. But with moves like these, this tractor tug is destined for something more. When it's not managing this massive parking lot, it goes out to meet ships and guide them through narrow harbor entrances. If it needs to slow them down, it just hangs on with the winch, pulls the other way, and becomes an aquatic emergency brake. To be effective, escort tugs require advanced engineering, starting with these azimuth Z-drive thrusters. Thrust comes from huge propellers. These cones increase their power. And the whole rig can spin a full 360 for total control on the water. They allow an experienced hand to steer on a dime, move forward, backward, and sideways. Two controllers, each connected to a Z-drive. Twist the control to turn the blades. Push them forward to control thrust. Commands are sent electronically to two sets of gears, an outer ring gear that controls direction, and an inner drive shaft that connects the engine to the propeller blades. The azimuths are great for pushing around boats, But they're even better when teamed up with the tug's powerful winch. Driven by a large 250 horsepower motor and equipped with a 300-meter fabric line, it's light enough to float, and unlike steel cables, it doesn't rust. This rope is so strong, you'd need the thrust of 10 F-16 fighter jets to pull it apart. And that comes in handy for this tug's most advanced move. It starts by hooking up to the back of a ship, then moves out to one side. And finally, with the help of its powerful drives and front keels, digs in and rotates the ship like a giant rudder, turning vessels 10 times faster than it ever could with a simple push. Tugboats may look small when sitting next to mega ships, but they're all muscle and fancy footwork, helping take goods out and bringing them in. A big gear in our economic engine. This may be the most popular machine ever designed for kids and the young at heart. Carousels have been enchanting riders for hundreds of years. Let's see how they work. Crawl inside one of these things, and you learn that there's no magic making it go round. It's a mechanical monster with pretty cool secrets. To start with, let's look at how the machine goes round and round. A lawnmower-sized engine turns a shaft that drives a small gear that grooves around the inside of a large planetary gear. That's all it takes to spin 10 tons of machinery. The seamless sets of teeth meshing together upgrade the small motor's output into all the force required to run the show. The gears are incredibly durable, and their smooth interlacing ensures that turning doesn't make the machine wobble. There aren't any wheels under this ride's 36 horses, so it's critical that everything stays in balance. To stabilize the carousel, a center pole connects to these beams called sweeps. Cables hold up the sweeps from above, like a miniature suspension bridge. Everything else is connected and hangs on for the ride. The center pole is locked in place by two variable beams called mudsills. These allow the ride to be quickly and easily leveled by adjusting one side or the other. And keeping things level is key to the machine's smooth reputation. The animals also play a part in this delicate balancing act. Each horse has a partner whose movement has to be mirrored on the opposite side of the ride. When one goes up, the other has to go down, or the ride will start to vibrate. So on this machine, that means 18 pairs of synchronized horses that are connected to hooks on a crankshaft. The crankshafts are connected to bevel gears that transform round and round into up and down. The horses themselves may look heavy, but on a traditional carousel, they're hollow and carved from material like basswood, as strong as it is light. Once everything is up and running, there's very little friction for the machine to overcome. So the ride could technically spin fast enough to throw riders from their saddles. Good thing this magnetic counter cuts off the power if the carousel cracks a breathtaking 11 kilometers an hour. A lot of people are curious about the lights. How the heck do you rig a spinning platform without tangling the wires around the pole? Think about your lit-up Christmas tree. Try spinning that for a couple of hours. What a mess. For a carousel to keep them on and the ride moving, it needs a specialized component that allows the machine to have electricity without wires wrapping around the pole. It's called a commutator, and it works by transferring electrical current wirelessly to metal brushes that spin along with the rest of the ride. Power enters the carousel through the main pole. It then travels through the commutator to the brushes. Current then flows to an electrical panel that sends it along wires to power the lights. Which on this particular machine has been happening since its creation in 1908. That's a long time to be spinning, but the carousel itself dates back to the Middle Ages. The ride's hundreds of parts make enough racket to sound like a medieval battle, which is spot on, because this gentle ride was first built as a machine to train knights for war. Centuries ago, young riders in training rode a merry-go-round for target practice. From a wooden horse, they tried to spear brass rings. It's where "reach for the brass ring" comes from. Thanks to an ageless design that keeps it going round and round, these young riders can dream all they want about faraway castles and have a great time while doing it.